Okay. All right. So, as we discussed earlier, so in Fourier series or Fourier transform, so there is a condition that it has to be satisfy the Dirichlet conditions. Okay, so that we call the convergence of the Fourier series. Convergence of the Fourier series. And the associated problem with Fourier series is nothing but if xt is discontinuous while each of its harmonic component is continuous, right? So when you say x of t, we approximate the x of t with the help of some sinusoidal components of harmonic nature. Okay, so these sinusoidal components are these are continuous in nature, right? But this x of t can take any kind of shape. It may be discontinuous or it may be continuous. But this is a difficulty when you approximate any signal of discontinuous in nature with the help of its harmonic components of the sinusoid components. Okay. So if you look at this approximation of this x of t, okay, so this x of t is the help of Fourier series. I can write x n t, so it is summation k equal to minus n to n a k e to the power j k omega 0 t, and omega 0 is the fundamental frequency, and its harmonic is multiplied with k, okay, k omega 0. So with multiple harmonic sinusoidal component you associated with its Fourier coefficients, so if you add up together, that gives me the approximation of the x of t, x of l, right? So since this is approximation of this x of t, so there must be error. So that error can be written as et, which is nothing but x of t minus x of nt. This is the approximation of this x of t. So this is the error, and I can write like this. So if I go on increasing the n, that means the number of sinusoidal components that I'm using to approximate this x of t, then this error e of n will be reducing towards 0. Okay. So that is our goal. So when this error is 0, then we can say this approximation of this x of t with the help of this expression is perfect. Okay. So that means the error can be written as is the summation of error square. Okay. So et square dt. So this error will be decreasing when n is increasing. So n is nothing but the number of terms, sinusoidal components that you are using to approximate the signal, right? So as n increases, these terms are the new terms of the sinusoidal components are getting added, and this error is decreases. So in fact, if x of t has a Fourier series representation, then the limit en as n tends to infinity is 0. Okay, so as much number of sinusoidal components we are going on accumulating, so the error between the original signal and approximation 1 will be going to 0, right? So this is very important. So if x of t is square integrable, then if this x square t dt is less than infinity, then et square, okay, e square also the integration over t, so it also goes to 0 as n tends to infinity, right? Okay, so the signal to be absolutely this would be square integrable. Okay, so this condition is defined by Dirichlet, and we call the Dirichlet conditions for Fourier series. That means for a signal x of t, so its Fourier series or Fourier transform can be found out by if it satisfies the Dirichlet condition. So the first condition that we discussed earlier. So over any period, x of t must be absolutely integrable. So that means summation of x of t dt, it should be less than infinity. So this is very, very important. So we say it is absolutely integrable. Okay. So that means the mod of ak should be also less than infinity. In the other way, we can say the mod of AK, which is the Fourier coefficients, also it has to be infinity. So then we see that this x of t, only the absolute summable is not a sufficient condition. Then we go for the square summability. Okay, so that means it should be over t mod of x of t square dt. It should be less than infinity. Okay, so it is called absolutely. This is square summability. Square summable. Okay. So this is one condition. Now, if you see this signal, this is a periodic signal that violates the first Dirichlet condition. That means if I take x of t is 1 upon t. Okay, so this is the signal. Now, if you look at this signal is a periodic of a fundamental period of 1. Okay, so this signal is getting repeated after this 1 to 2 the same thing, and 2 to 3 this is same thing. So this is the signal x of t, which is defined as 1 upon t. Now if you summation this one, go on summing this x of t within this period 0 to 1, now you see it is going to infinity. Okay, so it go on like this parallel to the y-axis. Okay, so that means this is not a convergence signal. So it is going to diverge if you go on adding up all the values, or if you go on taking the integration over 0 to 1. Okay, so that means this is not absolute summable signal. So this is the Fourier transform of this may not exist. Okay, this is the first Dirichlet condition. Then the second one, it says that any finite interval of time x of t is of bounded variation. That is, there are no more than a finite number of maxima and minima during any single period of the signal. So that means a single period of the signal for a periodic type. So there should not be more than a finite number of maxima and minima. This is very, very important. So this is an example. X of t is equal to sine of 2 pi by t, and t is defined as 0 to 1 if this is one period. Okay, so it satisfies the condition 1. That means it is absolutely summable. So that means if you take the summation, the integration over 0 to 1 x of t dt, it's less than 1. Okay, so that means it is absolutely summable. But if you see, there are so many maxima and minima. Okay, so you see there is so many maximas over here. Okay, there are so many minimas over here. So that means there is too many maxima and minima, or too many fluctuations of the signal in positive side and the negative side present in one period. Okay, 0 to 1 if you take one period. So here so many maxima and minima. So it is not satisfying the condition 2. Okay, so the Dirichlet condition 2 says that it should have finite number of maxima and minima in one period or over a finite interval of time, right? And the third one, in any finite interval of time, there are only a finite number of discontinuities. There should be a finite number of discontinuities in the signal. Okay, so furthermore, each of these discontinuities is finite. Okay, so now if you see this x of t, so this is a periodic signal over period 0 to 8. Okay, so this is one period. So within this period, so if you see, there is so many discontinuities. Okay, so here, then here, then here, here. Okay, there are so many discontinuities, which is not also satisfying the condition of Dirichlet, so that we can find out the Fourier transform of this x of t by using the Fourier series expansion. Okay, so there should be finite number of discontinuities. So there should not be more number of points where you go on discontinuous of the signal. So these are the three different Dirichlet conditions. If the signal satisfies these conditions, then its Fourier transform exists. Okay. So first one is the signal should be absolutely integrable or absolutely summable, and the second one there should be minima, like the finite number of maxima and minima within one period or within a certain time interval. And third one is there should be finite number of discontinuities, right? Now, for a periodic signal that has no discontinuities, if you see the periodic signal that has no discontinuities, the Fourier series representation converges and equals to the original signal at every value of t. So this is very, very important point. So for any periodic signal, so we find out its Fourier series. So if the periodic signal is no discontinuity is present, then its representation using Fourier series will be converges, and we can find out its exact representation in the Fourier series domain, right? Then for a periodic signal with a finite number of discontinuities in each period, the Fourier series representation equals the signal everywhere except at the isolated point of discontinuities. So except at the point of discontinuities where we have a discontinuities of the signal, or that we have isolated points, so we cannot find out this Fourier series. Okay, at which the series converges to the average value of the signal on either side of the discontinuity. So at the point of discontinuity, it is converges to the average value. Okay, that's the case. Now, in this case, the difference between the original signal and its Fourier series representation contains no energy, and consequently, the signal can be thought of as being the same for all practical purposes. Okay, so that's why we should not allow more number of discontinuities one period or within a finite interval of time. Okay, so we should not allow more number of discontinuities. Now, if you see, so a square wave. So if you represent the square wave is a periodic wave. Okay, so then if you try to represent this one using Fourier series, so that means we are going to add up all these sinusoidal components. Okay, so you see this is one sinusoidal component, the top one having a fundamental period. Then it's a harmonic of second one is the harmonic of the first one. The third one is some other harmonic of the first component. Then the fourth one is some other harmonic component of the first one. So when you go on adding up all this sinusoidal components with multiplication with Fourier coefficients, that leads to this last one, which is nothing what we call the square wave. It looks like a square wave. But if you see in the square wave, we are not getting exactly a constant value in the upper side as well as in the bottom side. Okay, so there is a ripple. Okay, there is a ripple because of this kind of sudden jump or sudden discontinuities over here. Okay, so over here, so this error when you go on approximation of this point of discontinuities. So when you go on approximating using the addition of all these sinusoidal components, so there remains some error, and the error is getting rippled, and you see the ripple or fluctuation in the top portions of the square wave. Okay, so this phenomenon we call it the Gibbs phenomenon. So that means when you go on approximating any sudden jump or sudden changes, so at the point of discontinuities or the point of where we go on sudden changes, so we'll find some ripples. Okay, overshoots and undershoots are the point of discontinuity. So that means here you see, so we find some kind of overshoots and undershoots, and that go on ripple. Okay, they go on fluctuating over the discontinuities. Okay, and this error or this ripple is going to be less when you go on increasing the number of sinusoidal components that we are using for representation of the signal. For example, if you take one sinusoidal component, so this square block, okay, so from minus t1 to plus t1, this square block is going to approximate like this. And if you look at n equal to 3, this one is there's some error is getting propagated over here. And if you go on increasing n equal to 7, so there is some more error, and when n equal to 19, so the error is going to reduce. Okay, so that means if you go on increasing the number of sinusoidal components, so then we'll be approximating the discontinuity part bit clear, but still there will be some error or ripples. Okay, so that means we are saying that in the spectral domain, so there is a leakage of spectrum. Okay, there is a leakage of energy from this point onwards. Okay, we don't want this energy should be leaked out from this, because this is a discontinuous, so it should be in the Fourier domain also it has to be represented here like this. Okay, this should not be go beyond this. So if some energy is getting leaked, so that means because of there is a discontinuities, and the Fourier series or Fourier spectrum is not going to approximate these discontinuities in a better way. Because of that, there is a leakage of energy, which is termed as a Gibbs phenomenon. Okay, Gibbs phenomenon, right? So the implication is that the truncated Fourier series approximation x of nt, the truncated Fourier series approximation of a discontinuous signal x of t, will in general exhibit high frequency ripples and overshoots. Okay, overshoots of xt near the discontinuities. Okay, so which you can see here. So there is a high frequency ripples. Okay, frequency ripples over the point of discontinuities. Such an approximation is used in practice, and a large enough value n should be chosen so as to guarantee that the total energy in these ripples is insignificant. So you need to look at this n. So that means how many number of frequency components that you are using to represent this x of n at the point of discontinuities. It is very large. Okay, so very large means so large number of harmonic components that you are using. So that means we are looking at high frequency components to represent this discontinuities, right? Okay, is it clear? Or if you have any doubt, you can ask me now. So this is the Desolate conditions. Okay, for satisfying that a signal should have a Fourier transform or Fourier series representation. If you don't have any queries, so let us move further for the properties of continuous time Fourier series. This property also holds good for the Fourier transform also. Let us look at the Fourier series, the properties. Suppose x of t is a periodic signal with period t, and fundamental frequency is omega 0 equal to 2 pi by t. Then if the Fourier series coefficients of x of t are denoted by ak, so ak are my Fourier coefficients, that is multiplied with the each sinusoids. So then x of t, we go on finding out the Fourier series, will land into ak. So ak is nothing but the frequency information, the k number of frequency components with amplitude ak or magnitude ak, that is associated with its corresponding frequency, kth frequency, to represent this x of t. Okay, so that is nothing but the Fourier series representation. So from x of t, you go into x of ak, or sometimes you will find many books they write it x of k like this also. Okay, so that means this one is the Fourier domain representation, and k is the number of frequency. Okay, so frequency components. So this is the forward path. So from x of t, we go to Fourier domain ak. Then from ak also using inverse Fourier series, so we can go back to x of t. So that's why it is bidirectional. So you see there is a arrow mark from both sides. Okay, so that means from x of t to I can go to ak, from ak to x of t also, right? And then let us see how what are the properties of this Fourier series it satisfies. So it satisfies the linearity properties. It says that if x of t one signal, and I found its ak is Fourier representation, And then is a second signal y of t. Its Fourier series gives me vk, right? So now if zt is another signal, which is a combination of x of t and yt in this fashion, so a into x of t plus b into yt, then if I take the Fourier transform of that, which gives me ck, which is nothing but the same amount of multiplication factor ak into a into ak and b into bk. Okay, so this would be my linearity superposition principle. It satisfies. Okay, so adding many signals together, then finding out Fourier series is nothing but it is the summation of individual Fourier series of particular individual components, right? So this is the linearity property that is satisfied. Yeah, so this is the proof that that linear property is satisfying. So x of t Fourier series gives me ak, y of t gives me vk. So ak is nothing but 1 upon t integration x of t to the power minus j omega t dt. So vk is 1 upon t yt into e to the power minus j omega t of dt. So ck is nothing but similarly, so you can find out the Fourier series by 1 upon t integration jt to the power minus j omega t. So zt I can put this as a into x of t plus b into y of t, then e to the power minus j omega t dt, and then I can take split out this integration over this addition, so that will be 1 upon t a into x of t into e to the power minus j omega t dt plus 1 upon t b into integration over t yt into e to the power minus j omega t. So this one is nothing but bk. Okay, so this one is my bk, the Fourier series representation, and this one is my ak. Okay, so ultimately I am getting a, capital A into ak, capital B into bk. So this is nothing but we call it the Fourier series representation of the ck, which is nothing but the addition of x of t plus y of t, right? So this is the proof for that the Fourier series linear. Okay, it satisfies the linear property. Then time shifting property. This is one of the important property of the Fourier series. So x of t gives me x of a of k. So then if I shift this x of t by t0 amount in the time domain, so x of t minus t0, then if I take the Fourier series, so that will be nothing but e to the power minus j k omega 0 t0 into ak. So this is the multiplication factor with ak that will get. Okay, I get my point. So this is very important. So any shifting to the time domain, so that gives me multiplication of this this factor e to the power minus j k omega 0 t0 with the Fourier coefficients ak, right? So yeah, so that the proof can be done by taking bk equal to 1 upon t x, integration over t x of t minus t0 e to the power minus k omega 0 t0. Then if I take tau equal to t minus t0, so the integration will be this one. Then if I simply take it out e to the power minus k omega 0 t0 outside, and then it will be 1 upon t summation over time period t x of tau e to the power minus j k omega 0 tau. So this one is nothing but we can say ak, right? So this is nothing but the ak of x of t. So then we can write this e to the power minus j k omega 0 t0 ak. Okay, so this means like shifting the signal by t0 amount in the time domain, it is equivalent of multiplying this component, okay, e to the power minus j k omega 0 t0 into the Fourier coefficients of the x of t, right? This is very important concept, time scaling. Okay, time scaling concept. Then time reversal. This is another property of the Fourier series. So time reversal, it says that x of t gives me ak Fourier series, then x of minus t, which is nothing but the folding operation or time reversal, that also gives me a of minus k. Okay, so x of minus t using the Fourier series, so it will give me a of minus k, right? So you can look into this. This expression x of minus t is nothing but summation k equal to minus n into infinity ak e to the power minus j k 2 pi t by t capital T. And if I take k equal to minus a, then the integration nothing but it goes the summation goes from m equal to minus m into infinity a of minus a, okay, into e to the power j m 2 pi by t by t. So now this is nothing but my Fourier series coefficients. Okay. So that means if I go on time reversal again, just nothing but whatever the frequency component, what is the amplitude, that will be same amplitude, what the frequency will be negative. That means there is a phase shift. Okay. So time reversal applied to a continuous time signal results in a time reversal of the corresponding sequence of Fourier series coefficients. So the Fourier series coefficient also it will be reversed. Okay, it says that it's a also it is a reverse of the Fourier series coefficients. So an interesting consequence of the time reversal property is that if x of t is even, okay, if x of t even, that is x of minus t equal to x of t, okay, if it is an even signal, then its Fourier series coefficients are also even. That means a of minus k equal to a of k. Okay, this is very interesting observation. So if it is an even signal, then a of minus k equal to ak. So it doesn't matter. So if it's an even signal, so if you take the time reversal also, you will get the same coefficients. Okay. Similarly, if x of t is odd, then that is x of minus t equal to minus of x of t. So this is the odd property. Okay. So if the signal x of t is odd, then so are its Fourier series coefficients. That means a of minus k is nothing but minus of ak. So it will get the negative magnitude coefficients. Okay. So this is the time reversal property of Fourier series. Then time scaling. Okay. So if x of t gives me a of k, then if I multiply some scalar factor, so alpha into time index t, so x of alpha t is nothing but summation k equal to minus m into infinity ak e to the power j k alpha omega 0 t. So that means the Fourier coefficients have not changed. Okay, the Fourier series representations has changed because of the change in the fundamental frequency. So only thing that you will have the change in the fundamental frequency, but the Fourier coefficients or the Fourier series coefficients, they are not changed. Okay, so when you go on scaling of the signal x of t. All right, is it clear? Then multiplication property. So that means x of t gives me a of k, then y of t gives me b of k. So then if I multiply x of t with y of t, okay, this is just a multiplication, then that gives me in the Fourier coefficient. So h of k, which is nothing but summation l equal to minus m into infinity a l into b k minus l. So this looks like a convolution operation. Okay, so this looks like a convolution, isn't it? This is one of the most widely used property of Fourier representation. So that means discrete time convolution of the sequence representing the Fourier coefficients of x of t and the sequence representing the Fourier coefficients of yt. So that means if two signals are multiplied in the time domain, and its consequence is that in the frequency domain, its individual Fourier coefficients that will be convolved. Okay, so that means a convolution of ak into bk. Okay, so this is the convolution equation. So this is very, very important property. So that means I can say multiplication multiplication in time is equivalent of convolution in frequency or in a Fourier domain. Right? Okay. So this is very, very important, and this is most widely asked questions in the quiz and in the interview board also. Okay. So this property, very widely used property in signal and system analysis. So multiplication in time, that is nothing but equal to convolution in frequency. And also it is vice versa. If I go on convolution of time domain, so that means x of t will be convolution with y of t. Okay, so that is convolution. Okay, so if I write z of t is equal to nothing but x of t convolution of yt. So now if I take the Fourier series or Fourier transform, so that is nothing but ak into bk. So this multiplication in frequency. There is multiplication in frequency. Okay, so these two are very, very important observation. Like multiplication in time is nothing but convolution in frequency domain, and convolution in time is equivalent of multiplication in frequency domain. Okay, so you go on multiplying its individual Fourier series of each component in the time domain. Okay, so this is very, very important property of Fourier representation. Then conjugation and conjugate symmetry. So like if x of t gives me a of k, then if I take the conjugate of this x of t, if it is a complex signal, so it is, if I take the conjugate of that, then it is nothing but the conjugate of a of minus k. Okay, so it is just a little bit tricky over here. So it will be nothing but conjugate of a of minus k. So here it is a proof that x of t can be written as summation k equal to minus m into infinity ak e to the power jk omega 0 t. So this is a Fourier series representation of this continuous time signal x of t. Now this, if it is x of star t, so it is a conjugate. So I can write this one as summation k equal to minus m into infinity ak conjugate e to the power minus jk omega 0 t. Okay, so then I can put this one in other form. So I can take ak minus k a of minus k conjugate e to the power jk omega 0 t. So which is nothing but this one is the Fourier coefficients or Fourier series representation. Okay, this is the Fourier series representation. That's why x star t, okay, the complex conjugate of the signal x of t gives me the conjugate of the negative frequencies of the Fourier coefficients. Okay, so this is called the conjugation. This is also one of the widely used property of Fourier transform of Fourier series. Okay, now if x of t is real, that is x of t is nothing but equal to the conjugate of that. So if x of t is real, then a of minus k equal to a star k. Okay, so if x of t is real and even, then ak is equal to a of minus k. That's the thing that we have already discussed in the earlier properties. Okay, so that means ak will be ak star, right? If the signal is real and even. Okay, so that is if x of t is real and even, then so are its Fourier series coefficients. That means the Fourier series coefficients are also, it will be real and even. Okay, similarly it can be shown that if x of t is real and odd, then its Fourier series coefficients are purely imaginary and odd. Okay, so this is one of the important property. So if x of t is real and odd, okay, it is odd signal, then it is coefficients are also imaginary. It will be imaginary and odd. Okay, this is one of the important property of the Fourier series. Okay, so next one is Percevals relation for continuous time periodic signal. So what is Percevals theorem says that? So Percevals theorem that means it says that the energy is conserved. Okay, so energy is conserved in the sense that what is the energy present in the signal in the time domain? The same energy we can find out of the Fourier domain. Okay, from its Fourier coefficients. The energy representation of the signal in the Fourier domain it will be same as the energy in the time domain. Okay, so this is one of the most important property which is called the Percevals theorem, and it is also widely asked questions in the interview board, and also maybe find in the quiz. So Percevals relations for a continuous time periodic signal is defined as 1 upon t, so integration over t x square dt. So this is the energy in the signal in the time domain, and it is equal to the summation of the ak square. Okay, summation of the Fourier coefficients. K goes from -infinity to infinity. Okay, so that means this is the energy in the frequency domain. This is the energy in the time domain. So both are equal, both are same. So that means the energy is conserved. Only thing that we are representing this x of t in terms of ak in Fourier domain. Okay, is it clear? So you can prove it like if you take this one, the energy in time domain. So it is 1 upon t integration over t. So ak e to the power jk omega 0 t square. Okay, so this is nothing but the Fourier series representation of x of t. And if you look at this one, then ak square. Okay, so integration ak square, and then e to the power j k omega 0 t square. So this function e to the power, then it will be e to the power j 2k omega 0 t. So this function is value is always 1. So that's why this integration is nothing but integration ak square dt. So which is nothing but ultimately we'll get ak square. Okay, so this is the energy in the frequency domain or the time domain, and this is the energy in the sorry, this is the energy in time domain, this is the energy in the frequency domain, right? So ak square is the average power in the kth harmonic component of the x of t, right? So when we use the kth harmonic component to represent x of t, so what is the power, average power over that? So that if you want adding together, so that is nothing but equivalent of taking the energy in the power in the time domain. So Percevals relation states that the total average power in the periodic signal equals to the sum of the average powers in all of its harmonic components. Okay, so total average power in the periodic signal in time domain is nothing but equal to the sum of the average powers of all of its harmonic components. So that means it's a summation of ak square. Okay, so kth harmonic component, what is its average power? If you sum up all together, so that means nothing but the average power of the periodic signal in the time domain. Okay, so this is called here Percevals relations. That means the energy is conserved. We say it is the same energy what or the same power that we have in the time domain. The same power also we can infer from its frequency domain also. Okay, and yes, these are the some of the properties of the Fourier series. Okay, now let us look at some of the important functions. So which is signum function. Signum function we have already discussed. So it is k. It is signum of t is 1 if t is greater than 0. It is 0 if t equal to 0. So then minus 1 if t less than 0. Okay. So this is a signum function. This is a sampling function. The sampling function is nothing but defined as sine of x by x, and its value is 1 at x equal to 0. Then it have a 0 crossing at pi and 2 pi. Okay, 3 pi, 4 pi. So harmonics of pi. This is the sampling function. Then a sinc function. Sinc function is the representation like sine pi x by pi x. Okay. So if you put here pi, add up here pi with x, so that it becomes the sinc function. So sinc function has similar nature of the sampling function. So here it is x. It will be again it is 1. The time crossing is 1, 2, 3, 4 like that only, and the amplitude is go on slowly decreasing. It goes to infinity, and its value is 1 at t x equal to 0. So this is sinc function that we have already discussed earlier. Then this is rectangular pulse. Rectangular signal is defined as like rect t by tau. Okay, so rect t by tau is nothing but a into rect t by tau is nothing but a is nothing but the amplitude of the rectangular functions, and this varies the amplitude from minus tau by 2 to plus tau by 2 and 0 otherwise. So here it is value is a, then after minus t by 2, so it is value 0. After plus t by 2, the value is 0. Okay, so this is a rectangular function. Okay, and it is defined like this. So rect of t by tau. Okay, so a is multiplied over here means so amplitude is a. Otherwise, if no amplitude is multiplied over here, so if it is only simple rect t by tau, so then amplitude will be 1. Okay, so it is if I multiply like this t by tau. Okay, so then the function will be nothing but it is amplitude is 1, and it is value from tau by t to tau by 2. Okay, so this is t. So this is the rectangular function defined in mathematical equation. Okay. Similarly, the triangular function. So triangular function we write a into triangle of 2 t by 2 tau. Okay, so this is the mathematical representation of the signal. So whenever it is given like this, so or a into tri, so it is triangle a into triangle t by 2 tau. Okay, so this is the in general representation of the function. So it represents that the magnitude is a at t equal to 0. Then it starts decreasing and go up to tau in the positive side and minus tau in the negative side. So that's why the length is here 2 tau. So that's why it is written a into delta t by 2 tau. Okay. And this can be also mathematically represented as a into delta t by 2 tau, a into 1 minus mod of tau by tau, mod of t by tau when t less than tau, and 0 when mod of t greater than tau. Okay, so this is the mathematical function of the rectangular pulse. So if a is 1, okay, nothing mentioned, nothing multiplication is here, so its amplitude at t equal to 0 is 1. Okay, if it is some scalar value is multiplied with the delta function, that means we will have a that amplitude over here. Okay, and if you see the triangular t is in general represented as 1 minus 2 mod t when mod t is less than half and 0 otherwise, and this is the representation of this in general. Okay, if nothing is mentioned over the denominator and in the scalar part, so if it is triangular t, its representation like this. Okay, so this is the some notation of the basic signals that you may encounter while you go on finding out its Fourier series representation. So is it clear? So this is all about the properties of the Fourier transform, Fourier series. And if you have any doubt, you can ask me now, so I'll clarify your doubt. Is anyone having any doubt or confusion up to now, what we discussed? If not, then I'll wind up the class over here. Ayush Raju. Ayush Raju. Do you hear me? Harsh Misra. Harsh Misra. Do you hear me?
Yes, sir. Yes, sir.
Do you understand what we discussed?
Yes, sir.
Okay, good. So you can go through the books of Simon Hykin or that other book, textbook, and then there you solve some examples that utilize this Fourier series properties. Okay, because that is very important. Whenever there is a complex task is given to you, complex function to find out its Fourier series. So directly evaluating the Fourier series, it will be very tedious task. So to avoid the complexity, so we can use the properties of this Fourier series to find out the answer for the Fourier representation of that complex signal. Okay, so that's why learning the Fourier, the properties of the Fourier series is very, very important. Okay, so if you have any doubt, you can ask me now. Otherwise, I'll wind up the class over here.
No, sir. No, no doubt.
Okay, so yeah, then this is the end of today's class. So we'll meet in the next class with, and then there we'll discuss some more properties, important properties of Fourier transform. That today we'll discuss, that is the properties of Fourier series especially, and we'll discuss the Fourier transform properties, and the same it will be similar also there. Okay, but I'll overlook into the properties of the Fourier transform. Then I'll discuss some more insight into the Fourier transform concepts and there, and hopefully we'll do some problems based on the properties of the Fourier transform. Okay. Okay, sir. Then this is the end of today's class. So now you can leave the meet one by one.